Hello. In this video I'm going to talk about the very simplest kinds of antiderivatives and to begin the process of building up some technical skills for general integration. The indefinite integral, written as the integral sign without any limits at the top or bottom, stands for the general antiderivative of f of x. And so when we talk about the integral of f of x, we are usually just meaning the antiderivative of f of x. This means that for some function capital F of x, we could write the integral of f of x dx as capital F of x plus a constant. The constant here is called the constant of integration. And what it stands for is the fact that by adding a constant to the antiderivative, you get a new function which is still an antiderivative of the one that you started with. So capital F of x plus any constant will have the same derivative equal to little f of x. We use that constant of integration whenever we're using integrals to find solutions to models that are differential equation models, and we need the c to adjust our solution so that it matches our boundary value conditions. The overall strategy of integration is to reduce whatever integral you have to simpler integrals, then maybe further reduce those simpler integrals to even simpler integrals until finally you get to something that you recognize, and where that means that you can actually figure out what your integral is. Now, to make this strategy work, you have to have some integrals that you do recognize, and I want to just start you on the process of building up this collection of integrals that you know immediately how to evaluate. Basically, if the more that integrals that you have memorized, the quicker you can do other integrals. So let's look at these simple examples. The integral of a power of x to the m dx is simply 1 over m plus 1 x to the m plus 1 plus the constant of integration. To see that this works, just take the derivative. Take the derivative, we get m plus 1 comes down and it cancels out here, and we subtract 1 from the exponent, so we just get x to the m. So we can see that this is the most general antiderivative of x to the m. So that's what that integral is. The integral of 1 over x dx is just log x plus a constant, because the derivative of log x is 1 over x. Now what about this simple example? Well, you may not know this, but in fact the integral of 1 over x plus a dx is the log of x plus a. How do I know that? Well, you take the derivative. What is the derivative of log of x plus a? Well, it's a chain rule. We have x plus a substituted into the logarithm, so we get the derivative of log, which is 1 over. So we get 1 over x plus a, and we have to multiply by the derivative of x plus a, but that derivative is 1, so it disappears here. So the derivative of log of x plus a plus a constant is 1 over x plus a. And so if you recognize that as being how you integrate 1 over x plus a constant, that will save you time when you're doing more complicated integrals. Okay, let's do a few concrete examples. I'm going to do these 3 examples. The integral of x to the 4th plus 5x cubed minus 3x squared plus x plus 7 dx. We'll integrate x plus 1 over x dx, and we'll integrate x squared plus 1 over x dx. Now for the first integral, we're going to use this property that the integral of a sum of functions is the sum of the integrals. And so we can integrate x to the 4th and integrate 5x cubed separately and then add the answers together. So we just work our way down this polynomial, and we get 1/5 x to the 5th, 1 over 5 x to the 5th, which is the integral of x to the 4th. We get 5 over 4 x to the 4th. The derivative of 5 over 4x to the 4th is 5x cubed. We'll get here minus 3. There's a minus above, so we get a minus here. 3, and we divide it by 3 and have x cubed. So we add 1 to the exponent and divide by the new exponent. We have another name for 3 over 3, which is much simpler. And x has its antiderivative 1/2 x squared, and the antiderivative of 7 is 7x. Because it's a sum, we can do them all individually. At the end, we have to add the constant of integration to indicate that to get all of the antiderivatives, we would take that function and adjust it by a constant. Okay, so that's a simple kind of integral where we've used the basic x to the m formula over and over again. Let's look at this integral, the integral of x plus 1 over x dx. Again, it's a sum of two functions. The first one has its integral, the integral of x is 1/2 x squared. The integral of 1 over x is log x, and so we get the sum of two functions. And so this is equal to the sum of 1/2 x squared plus log x, and then again we add the constant of integration. And this is showing that when you have an algebraic integrand, something that you're integrating, you can get an antiderivative, which is the sum of an algebraic function and a transcendental function. And finally, the integral of x squared plus 1 over x can be evaluated by taking this fraction and splitting it up into the sum of two functions. So we have x, we can write it as x squared over x plus 1 over x. Now x squared over x is just x, and 1 over x is 1 over x. So this function that we're integrating could be written as x plus 1 over x. But that's terrific, because that's the integral we just did. So we know how to do that integral, and so we'll get the same answer. Now what this illustrates is that you may have to do a little bit of algebra in your integrand to get it into a form that you can recognize. So here we used algebra to move to a recognizable form. Up above we used the fact that we have the sum of integrands to split it into two, where we have a way of doing it. And up above there we actually did it by splitting it up into many different functions, each of which we knew how to integrate.